Morning, everyone. My name is Mary Jo Meissner, and I'm Vice President for Communications and Public Affairs at the Boston Foundation. The Boston Foundation is pleased to be the leading sponsor of this very important three-day conference on climate change, and this is the first session of day 3. What we're going to do today is look forward to the next century for this first session and talk about adaptation and mitigation. And we have 4 excellent speakers lined up for you this morning. We will allot time at the end of all of their presentations for about a half hour of Q&A with all the speakers, and I'll moderate that. But the speakers have they can go ahead and have a few questions and answers right at the end within their segment. And so with that, I'd like to introduce our very first speaker this morning, and that is Robert Armstrong. Robert is the co-founder of the Massachusetts Institute of Technology's Energy Initiative. He is the Chevron Professor of Chemical Engineering at MIT, where he has been on the faculty since 1973 and has served as the head of the Department of Chemical Engineering from 1996 to 2007. He was elected into the National Academy of Engineering I believe that was in 1992, and has won several other awards for the work that he has done in the fields of chemical engineering. He is going to speak to us this morning about technology pathways to reducing carbon footprint of our energy system. And with that, I'd like to ask Robert to come on up.
Just enjoying watching to see if I have slides.
Okay.
Well, good morning. Welcome to a nice warm day in Boston. So it's a pleasure to be here and have a chance to talk to you about the technology and climate change. As you've heard, can you hear me okay? Yes. Okay. So as you've heard in talks already in this symposium, you've learned a lot about the looming challenges of climate change. You've probably heard some, and you will hear more about policy solutions and way to address climate change through policy. What I'm going to talk about is what do we do in the absence of policy. I think you can't help but watch our system in the U.S. and notice that we're not jumping very quickly onto policy solutions to climate change. And so, at least for the immediate future, we are in a business as usual scenario. And if you look at projections going forward out to mid-century and beyond, if we were to stay on a business as usual scenario, then we're going to see significant increases in energy consumption, significant increases in use of fossil energy sources, roughly 80% fossil energy sources out to mid-century and beyond. And we'll see significant increases, of course, in CO2 in the atmosphere and associated increases in temperature. So I think the question is that we look as what can we do in the meanwhile? I mean, you do see progress in Washington. The EPA's proposed emissions regulations on power plants is certainly encouraging. But in the absence of a price on carbon, which will really help to reset the marketplace, what can we do? And I think one of the great options we have available to us is to take advantage of technology and what we can do with new innovation, research and development in technology to address climate change issues. I am certainly not standing here telling you this is the answer, because I don't think that's so. But I do think it's a strong contributor to the solution in any scenario you imagine. And I think it's a really important piece of the puzzle today, given the lack of significant policy. So I'm going to talk about technology options that we can employ today. 3 principal routes we can take with technology today. The first of those, the one in the top right here, is building efficiency, or efficiency more generally. So how can we get more use out of the energy we consume, get better use of it, so that we reduce the energy intensity of our system. Okay? And I'll give some examples there. A second approach we can use is fuel switching. Take advantage of the fact that we can move in some sectors, particularly power generation, from high carbon content fuels to lower carbon content fuels, and with the same production of electricity, have a smaller carbon footprint. And so I'll talk specifically about switching from coal to gas, which is certainly underway in the U.S. in a big way today. And then lastly, I'd like to talk about research and development to drive down the cost of low or zero carbon energy solutions. In the absence of a price on carbon, you'd love to be able to get there just through technology alone. If I could develop the magic technology and make a zero carbon energy system that's cheaper than fossil energy systems, then I would have a winner. I doubt we'll get there, but in any scenario, the lower we can get the cost through technology, the better off we are. So let me give you maybe half a dozen little vignettes of technology contributions in those three areas. So I'll start with the efficiency, because I think everyone agrees that this is the low-hanging fruit out there. There's a lot of disagreement over why we're not picking up all this low-hanging fruit, but it is there, and I think there's a lot of interesting technology we can apply to taking advantage of efficiency options. Here's an example of a way to take advantage of waste heat. This may not be something you think about every day when you get up, but it's a really important problem in the industrial sector and in the power sector in the U.S. and in other major economies around the world. Much of the energy we produce comes with it, brings along with it what we call low-grade heat. So it's heat and energy, but it's at such a low temperature that you can't do useful work with it. All right? And so it's generally just thrown away. It's exhausted into the air. It's exchanged with water for cooling, but otherwise lost. So a big question is, can you take that waste heat and use it as a source of important energy for useful applications? An instance you may all be familiar with there is combining power plants with district heating. If you take the waste heat that comes out of a power plant and you're close enough to residences or businesses that need heating for space heating, then you can use that waste heat from the power production for that domestic heating. This is an example of using that waste heat to improve the efficiency of battery storage. And here you take advantage of the fact that for rechargeable batteries, the voltage at which the battery works is different depending on the temperature. At high temperatures, you generally have lower voltage. At low temperatures, you have higher voltage. So the idea here is to heat up a rechargeable battery in step one. That's this piece here. Then when it's hot, you charge the battery at lower voltage. You cool down the battery, and then it will operate at higher voltage, and you discharge it. And so you get more energy out of the battery than you put in through the charging process. Right? And then you all get skeptical and say that can't be. You don't get more energy out of the battery than you put in. I'm told just through the charging process. The other energy comes from the heating step here. But you're using waste heat, low-grade heat, that otherwise you would throw away to the environment. This is work from a lab here at MIT, Gang Chen in mechanical engineering, and collaborators at Stanford University. But that promises to give, in the early experiments they've done, a 5 to 6% increase in efficiency of the battery system. And that could be very important for large-scale storage applications. Second example is how we warm buildings to make occupants comfortable. Generally what we do is, of course, heat the entire space in a building or well, certainly in New England, we mostly heat spaces. I think on a day like today, you think more about cooling, but in this example is focused on heating. And so there's a lot of space where there are no occupants at a given time, and so you're wasting all the heat you put in. Here's an idea that comes out of Carlo Ratti's Sensible City Laboratory here at MIT, where he takes advantage of the fact that we all walk around with a lot of Wi-Fi broadcasting equipment on us. And you can use that to track where occupants of a building are, and then use that signal to direct ceiling-mounted infrared heating sources to warm people where they are in a building. So you just warm locally around your environment. So a little bit like sitting outdoors at a restaurant in New England when it's a little bit too early in the spring, right? They have these little radiant heaters that they put over you. That's a way to take advantage of the localized heating capability, not waste heat elsewhere in the building. And with more information from your cell phone, you could actually tune the temperature you like as an occupant. So you can adjust the comfort level individually. Third example of efficiency is fuel switching. So here we want to take advantage of the fact that not all fossil fuels are the same. Some of them have a lot more carbon in them per unit of energy than others. And in particular, coal has the highest carbon content. Natural gas has the lowest. Interestingly, both of those are used in large quantities in the power sector. And so what we're looking at here is the opportunity to switch from coal to natural gas and save on our carbon footprint. To do that efficiently without a price on carbon, you need to be able to take advantage of existing infrastructure. If this meant going and building a lot of new natural gas-fired power plants, it probably wouldn't be economical. But it turns out that we have today, because of overexpansion in the 90s, the U.S. has a large excess capacity of natural gas combined cycle power plants, so-called NGCC plants. And you can see that in this top graph, which looks at, in the blue bars, the dark blue bars, the percentage of nameplate capacity for production of energy, and in the light blue bars, the percentage of actual output of energy from these different power plants. And you can see that there's a little bit better than 40% of the capacity for the power sector is in natural gas power plants, but somewhere in the low 30s is the actual output. At least that's as of around 2010 to 2011. Actually, that's 23%. Coal, on the other hand, has a lower capacity in terms of baseload capacity, but it's used more. It's used as baseload power capacity. So there's actually more electricity produced from coal in the U.S. Than by natural gas. But you see from the blue bars, there's the capacity sitting on the ground to make the electricity from natural gas instead, without building any new capacity. Right? It's just a matter of fuel switching. And in fact, we've seen that in the U.S. over the last couple of years, driven simply by the price difference in natural gas as more shale gas comes online. 2 years ago, natural gas and coal-fired power were almost at parity in the U.S. This past winter, because of the severe winter, natural gas prices spiked and coal went up a little bit relative to natural gas, but not to these previous levels. So we're actually moving in the direction of lower carbon emissions from our power sector simply because of price changes in the fuel system. Lastly, I'd like to look at low or zero carbon technologies for producing energy. And I'll use solar as the prime example here, because I think we all agree that solar is the big renewable resource we have. The problems with solar are twofold. One is how to make it cheap enough And the second is how to make it dispatchable. Right? So what do you do at nighttime, fundamentally? This is an example of a technology in solar called concentrated solar power, in which you take incoming solar radiation and you use mirrors to focus it on some receiver that gets really hot. And then you use that hot receiver material, it's generally a fluid that you heat up, use that to drive a power cycle, much like you would use you would use in a coal-fired power plant or in a natural gas power plant. In this novel arrangement for concentrated solar power, there's an arrangement of mirrors that you can put either on a hillside or in a flat plane, which beams solar energy into a big tank, which is full of molten salt. So you use something like a potassium, sodium nitrate mixture, which melts at very high temperatures. So it melts around 220, 230 degrees centigrade. And you heat that up to 550 degrees centigrade or so, which is near the upper limits of traditional steam power cycles. Right? So you heat this bath of fluid up. During the daytime, you can actually heat up excess fluid. So you can have what I draw as blue stuff at the bottom. That's cold fluid. Cold in this case is maybe 250 degrees centigrade. But then you heat it up with excess solar during the day to 550 degrees or so. Then when you need power, whether it's day or night, you can pull out hot molten salt. You can run that through a heat exchanger to produce steam to drive a traditional steam power cycle. And again, this is dispatchable because you can use it day or night. This overcomes a number of problems with today's concentrated solar power technologies. One being that you have built-in storage. Two being that with this molten salt, you can go to very high temperatures. You can go well above 600, which limits a typical steam power plant. And you can go to much more efficient power cycles. You can, for example, use what's called a Brayton cycle, which uses a gas as the working fluid. It's what's driving you when you're flying on a jet. That's the jet engines use a Brayton cycle. And that gets rid of water cooling problems, which are a big issue with concentrated solar. So there are interesting solar technologies on the horizon that promise higher efficiency and also dispatchability. The other big solar technology, of course, the biggest solar technology today is photovoltaic. And there are lots of different innovations underway with photovoltaics. An example I'm going to show here is a photovoltaic technology looking at the photovoltaic materials and the electrode materials, how to design those with material science to make them transparent. If you can make them transparent, then you can cover lots of surfaces we have around cities, like the glass in the John Hancock Tower, with PV material. The occupants still get light in to light their work, but you can make electricity from all of that surface area. Just to give you an example of this technology, you could also put this on your iPad or your cell phone so that you could charge your iPad or cell phone while you were working. Let's see. Is it working? Ah, here it is. Here we go. So this movie illustrates the transparency of the glass and the PV material. You can see that when you cover up the surface on this little cell phone, that the voltage drops there, so that in fact you are powering from the light that this is receiving. If you remove the glass cover, you can see that in fact it is transparent. Right. So we do have the technology to do this. We need to make it more efficient, to be sure. And we need, for building applications like a big commercial building, John Hancock Tower, you need better ways, better technology for connecting it to the building's electrical system. But I think there's a lot of promising technology there. The other challenge here with PV in particular is storage. So how are you going to store the energy for nighttime use? There's a lot of work in the battery space going on. This is an example of a novel battery system which uses two liquid electrode materials, or two liquid electrolytes, which rather than being separated by a membrane, which is typical in a battery like this, they are separated simply by the flow pattern. It's what's called a laminar flow pattern. So they flow side by side and don't interact over the distances of the battery. And with this technology, the researchers here at MIT, Martin Bezant and Cullen Bowie, have gotten to roughly 3 times the power density of previous hydrogen-bromine batteries, and they've gotten to a much cheaper system because they can eliminate a very expensive membrane. Last example is storage for wind, as another example for how we might do storage with intermittent renewables. One of the most attractive wind sources is offshore wind, because offshore wind velocities are generally larger than onshore, and they're generally more sustained. Okay? So it's a good place to put wind. It's also interesting in that it's easy to provide a storage solution with offshore wind if it's far enough offshore so you need to use a floating platform. If you have a floating platform, then you have to have some way to anchor or tether the platform to the bottom of the ocean. In this idea from Alex Slocum in mechanical engineering here, he uses a series of large hollow concrete spheres or structures to serve as anchors. And the idea is that when I have excess wind, I use the power I don't need to transmit to shore to pump water out of this big sphere. When I don't have enough wind, I can let the water flow back into the sphere and drive a turbine as it flows back inside. So essentially, I'm using the anchoring system as a pumped hydro storage system. It's much cheaper than trying to build a pumped hydro system on shore. So I've given you a couple of brief examples of technology solutions to moving towards reduction of CO2 emissions in the energy space. That's an example of game-changing technologies for improving the environment. These game-changing technologies in energy can also have a big impact on the U.S. and other nations around the world in terms of economic growth. They provide jobs for people to build these new devices, new industries. And I think it provides security in that it provides people around the world available energy that doesn't require the global transmission systems or trade systems that we often need. A message that I would like to leave you with is that one of the things I think we need in this country is more and sustained R&D spending to keep this pipeline of innovations in the energy space going. Just yesterday, we released a new book called Game Changers, Energy on the Move. This is an unabashed plug for this book, for which I get no royalty. So, but this came out yesterday. George Schultz at Stanford and us at MIT have put this together to provide a set of examples of how these game-changing technologies have already made a difference and will likely make a difference going forward. So with that, now thank you for your attention and leave you with this note that we can never be too complacent. I love Will Rogers' comment that even if you're on the right track, you'll get run over if you just sit there. Thank you very much. I think I used up my time.
Do we have, you
We might have time for one question before we start the next presentation. Is there anyone that's got a question for Robert? Right here? There's a mic behind you.
I was hoping you could spend a couple minutes talking about maybe Nocera's work on the photovoltaic and what about nuclear fusion? Like how far off would that be? Is that a possible game-changing technology that we'd see in the next decade or so?
So I'll say a few words about at least the first one.
Robert, if you could use the microphone because
Okay.
it's being recorded.
Okay. So let me say a few words about the first one. We don't have a lot of time, but with solar storage for solar energy, there are two timescales you have to worry about. One is day to night, and I think you could do that with batteries and the ideas I've shown. There's another storage timescale which is seasonal. How do you get from summer to winter, which in the northern hemisphere we're quite familiar with, but there's obviously a similar problem in the southern hemisphere. There's also the issue of how can solar make a difference in the transportation market, and there you have to electrify otherwise, and battery storage for cars is a challenge. There's some interesting ideas in the marketplace today. So I like the idea of using solar energy to produce hydrocarbon fuels renewably in the long-term future. Dan Nocera's work, which began here at MIT, now is at Harvard, takes solar energy and uses it to catalytically split water into hydrogen and oxygen. And then you can recombine hydrogen and oxygen in a fuel cell to produce electricity and water as a byproduct and recycle it. So the energy input is sunlight, and you make a fuel that can be used to make electricity on demand. And you can store the fuel as long as you want. The challenge there is that hydrogen isn't so easy to store, particularly for transportation applications. The best way known to man to store hydrogen is to stick it on a carbon. And there's a lot of interesting chemistry for doing that. And so you can use solar energy, thermal energy as well to do the reactions to put hydrogen on carbon and at the same time reduce carbon dioxide to these higher energy states. I think personally that's the technology of the future, but it's well out in the future. We're still in need of the right technologies there. So that's what I would call very early stage game changers work, but very important, I think, for the 15, 20-year time horizon.